Alright, hello everyone. So we started our lecture series about the second order differential equations applications with a example of a spring mass system where you don't have damping and you don't have driving force too, right? But now we are going to learn a little variation of that same example where you don't have damping again. Okay, that is why you don't see dx over dt term here, but you do have external force or the driving force in the system. So this is the differential equation. It's really the non-homogeneous version of the very first case that we learned in the lecture series. Okay, all right, now let's talk about it mathematically first, and then let's come to what is the physical meaning. Now this is very important. Within this problem we have several cases. Now let's say our driving force, or F, is a special function or a special driving force which is a sine or cosine function. Okay, so when you have a sine or cosine function, interesting thing happens, because if you want to solve this non-homogeneous differential equation, well, first you have to solve the homogeneous version of it. So the auxiliary equation is m square plus w square is equal to 0. Okay, so then the roots are, think about this, the roots of the system are going to be complex, and I'm not going to show you how I derive them. You should be able to do them now. Is wi. So beta is w and alpha is 0, right? Okay, so I did that fast. Okay, now the solution is going to look like, then x is equal to complementary solution, e to the alpha t, e to the 0 t is 1, so c1 cosine beta t cosine wt plus c2 sine wt, right? So this is just a general representation of what we get. We are not talking about numbers here. Now let's go back to the driving force. Now this is the solution or the complementary function solution for the homogeneous differential equation. But really we have a non-homogeneity here, right? And I said this non-homogeneous function is, for example, sine gamma t. That's the non-homogeneity. Let's say f is sine gamma t. Now how do you solve this problem again? Well, you have to come up with a guess for particular solution, right? So the guess for particular solution is, initial guess here is a sine gamma t plus b cosine gamma t, right? Which is something that we have seen several times now. Okay, now what is the next step you do? Well, we check for overlap. Don't forget that. Now, do we have an overlap when we compare xt or the complementary solution and the particular solution? What do you think? Well, we don't know. We could have an overlap. We might not have an overlap. What does decide the overlap? What is the thing that decides the overlap? Try to see. It's there. It's gamma and w. Do you agree? If gamma is really w, see, do you have an overlap? We definitely have an overlap if gamma is equal to w. But if gamma is not equal to w, then sine gamma t and sine wt are two different things. Cosine gamma t and cosine wt are two different things, because gamma is not equal to w means they are two different numbers. Okay, so we have to study two cases within this specific example. Right now, let's only study the case where gamma is not equal to w. Okay, that means where we do not have an overlap. Really, we start with a boring case, because then it's really boring when gamma is not equal to w. But when gamma is equal to w, or when you have an overlap, you will see in the next video lecture that it's very interesting. Okay, all right. So however, now that is the mathematical explanation. Now what is the physical explanation between, or physical explanation of gamma being equal to w? What do you think? Well, gamma being equal to w means gamma is coming from the forcing function, right? W is coming from the complementary solution. Complementary solution means free response, right? If you do not have an external force or a driving force, what happens? That is explained by the complementary function, or W, right? But gamma explains what happens when you have a driving force. Now, gamma equal to W means, listen to this very carefully, okay? Gamma is equal to W means frequencies of the free response and the frequency of the driving force are the same, okay? Then you have gamma is equal to W. But if the frequencies are different, then gamma is not equal to W. It will make huge sense in the next video, okay? So that's the physical explanation. Now in first case, or in this video, we really only concerned about frequencies being different. That means gamma is not equal to W. Let's look at an example. Okay, so I'm not going to solve it. I'm going to walk through it, and I will explain the physical explanation. Okay, so we have this differential equation. We write the auxiliary equation m square plus 2 is equal to 0. So the roots will be complex, plus or minus root 2y. Then the complement alpha is 0. My bad. Beta is root 2. So then the complementary solution is e to the alpha. E to the 0 is 1, so this is the complementary solution we get. Now we keep it aside and we write a particular solution. So our forcing function is sine 40. So our particular guess will be a cosine 40 plus b sine 40, right? So then do we have an overlap? No, right? Because gamma is not equal to W here. Gamma is root 2, okay? And W is actually W is root 2, my bad. W is root 2. Gamma is coming from the forcing function, which is 4. So they are not equal. So we do not have an overlap, right? Cosine 40 and cosine root 2t, that's different. So we keep our original particular solution and we find x prime and x double prime, and we substitute it into the differential non-homogeneous differential equation, right? So when you substitute, what we get is this long algebraic expression. So we collect the cosine 40 terms, find A, collect the sine 40 terms, find B. So we can find A and B. A and B are like this, okay? I suggest you to pause the video and try to do the problem by yourself. But anyway, so then the particular solution is A is 0, so B is negative 14. So we say A cosine 40 plus B sine 40, A is 0, so we do not have this term. B is 1 over 14, so it's negative 1 over 14. So this is the particular solution. And this is the complementary solution. So the final solution is complementary solution plus particular solution. Okay, so I'm really interested in what happens after that. Okay, all right, so now we use the initial conditions here in this final solution and we find C1 and C2. Okay, so if you find C1 and C2, this is the final solution I get. Okay, so now let's discuss here. All right, so what do you think? What is the limit in behavior? What is the limit when t goes to infinity? Now, what happens in this motion? This motion, you do not have a damping at first. We are talking about examples of no damping. So, energy does not drain away from the system. So, that means the motion will go forever, right? You can see this is a superposition of two sine curves or summation of two sine curves. And these sine curves are going forever. You can see this motion is periodic, okay? And yeah, so here the motion is really not determined by the particular solution, okay? Particular solution alone eventually. It's just a superposition of particular solution and the complementary solution, because the complementary solution does not have an exponential decay like the examples that we saw in previous videos, okay? So that's what happened in this case, all right? So the whole motion or the eventual motion is determined by both complementary solution and particular solution. The motion goes forever. The amplitude is bounded. That means we have some kind of a certain amplitude as a number. We will discuss why I said that term later, but It's just a superposition of two sine curves and the motion goes forever. Okay, all right, so let me finish on this note. You should be able to look at the final solution and looking at the scenario of the problem. Damping is there's driving force, and you should be able to argue what happens in every case. Okay, all right, so then yeah, that's it for this video. Let's see you on the next other video. Okay, all right, thank you.